Hi everyone, welcome to my video on logarithmic functions. In this video, we're going to talk about logarithmic functions in general as a review, and then we're going to look at how to find the derivative of a logarithmic function. All right, so logarithmic functions are the inverse of exponential functions. So fill in the blank here, the inverse of the exponential function is the logarithmic function. Now, the base of the exponential form is the base of the logarithmic form. So in exponential form, it might look something like this. 2 to the third power equals 8. In logarithmic form, it would look like this. Log base 2 of 8 equals 3. So the base is still the base, no matter which form. All right, the exponent of the exponential form is the answer of the logarithmic form. So if you notice, back up to my example, the exponent in exponential form is the answer in logarithmic form. And remember, because these are inverse functions, your inverse function switches your input and your output. So the independent variable of exponential form is the dependent variable of logarithmic form. Because again, it's going to switch your input and your output. Alright, or think of it in terms of domain, because that's your independent variable, and range is your dependent variable. So the domain of exponential form is the range of logarithmic form. Okay. So here we're just going to look at some examples on how to convert to logarithmic form. So when you're converting to a logarithm, I like to call it the drop and switch. Here's my previous example, 2 to the third power equals 8. That would become log base 2 of 8 equals 3. So you drop the base and then you basically switch your input and your output. To go back to our first example, 10 to the fifth power equals 100,000. That would become log base 10 of 100,000 equals 5. But when the base is 10, we call this the common log, and we typically don't write the base. So you'd probably see it as log of 100,000 equals 5. All right, for our next example, this would become log base 2 of 1/8 equals -3. Last one would be log base A of C equals B. All right, and then in these two examples, we're switching back to exponential form. So in that case, start with your base, 10 to the third power equals 1,000. So it's kind of like a circle. Or over here, 16 to the 1/2 power equals 4. Okay, so let's look at the graph of a logarithm. Now remember that these are inverses of exponential functions, okay? And so your exponential function, again, depending on your base, if the base was greater than 1, it looks like this. And if the base is a fraction between 0 and 1, then it looks like this. It was exponential decay. Okay, so this was for y equals a to the x when either a is greater than 1 or a is a fraction between 0 and 1. So this is what we learned in last night's video. Now, your logarithmic function is the inverse of your exponential function. So graphically, that means taking these two graphs and reflecting them over the line y equals x. Okay, so here's y equals x. So if I flip that graph over that line, I'm going to get this. And then over here, if I flip that graph over the line y equals x, I'm actually going to get this graph. So I hope you see the reflection, the flip over that line, y equals x, but the green graphs are the graphs of your logarithmic function, okay? So these would be for log base a of x. When a is greater than 1, it would look like this graph. And when a is a fraction between 0 and 1, it'll look like this graph, okay? So let's talk about the characteristics of the parent graph. Okay, so the domain of your logarithmic function is actually 0 to infinity. And your logarithmic function has a vertical asymptote at 0, okay? So your domain is 0 to infinity. The range is all real numbers. And this graph has a VA, which is x equals 0. Now, if you compare those to your notes from last night, looking at the characteristics of the exponential functions, you'll notice that your domain and range switch. And instead of an HA, there's a VA. And the intersect switches, that's important too. This graph has an x-intercept of 1, 0, where your exponential function has a y-intercept at 0, 1. Okay? All right, so which transformations will change the domain of a logarithmic function? So this time, because the domain is 0 to infinity, it's shifting the graph left or right that will change the domain, or flipping it over the y-axis. And then which transformations will change the range? Actually, none. It will always be all real numbers. Okay. All right, so let's look at an example of sketching the graph. We want to sketch the graph of log base 2 of negative x plus 4. And actually, before I even sketch that graph, I have to factor out this negative. So if I factor out the negative, that'll leave x minus 4 in parentheses. If you don't factor out that negative, you're going to get the shift left or right incorrect. Okay? All right, so our base is 2, that's greater than 1. So our parent graph looks like this. It'll get closer to the vertical asymptote. Our transformations, the negative on the inside is going to reflect the graph over the y-axis. And the minus 4 is going to shift the graph right 4. Okay, so I'm going to take this point at 1, 0, flip it over the y, so it'll end up here, and then move it right 4. So it'll end up here. And my VA is going to end up at 4, again, because we're shifting the graph right 4. And then because of that flip over the y, the graph is going to look like this. All right, so the domain, because we flipped over the y, it's now going to be negative infinity to positive 4 because of the right 4. The range, remember, is always all real numbers. And we have a VA, which is now x equals 4. Okay, now there are some properties of logarithms that you need to be familiar with. The first 4 are like basic properties. Number 1, if you are finding the logarithm, no matter the base, of 1, that will always equal 0. Okay, now this makes sense because no matter what the base is, if you raise it to the 0 power, remember that will always equal 1. Okay? Alright, our second property is, let's say you have log base A of A. Well, that would always equal 1 because A to the first power would equal itself. Now, remember that these are inverses. So, if you have a power base A raised to a logarithm base A, let's say of x, that would just equal x because these are going to undo each other. And then we could flip that around. If you have a logarithm base A of A to the x power, again, that will just equal x because they are going to undo each other. Okay? All right, and then there are 3 laws of logarithms, and this has to do with expanding and condensing logs, and it works like this. If you have log of x plus log of y, that will equal log of x times y. And if you have log of x minus log of y, that would equal log of x divided by y. And then the third one has to do with a constant multiple times the logarithm. And basically we can take that multiple and move it to an exponent, so this would equal log of x to the c power. And again, these 3 laws work for any base, so it doesn't matter what the base is. All right, let's look at some examples using the last 3 laws. We could use it to expand. So here, because we're multiplying a times b times c to the 6, this would expand into addition. Log base 4 of a plus log base 4 of b plus log base 4 of c to the 6th power. And then we can move the 6 down in front and make this log base 4 of a plus log base 4 of b plus 6 times log base 4 of c. All right. This next one, log base 3 of z cubed times the square root of x, first thing I would do is convert that square root to a fractional exponent. And then we'll expand. So, because we're multiplying, it's going to expand into addition. Log base 3 of z cubed plus log base 3 of x to the 1/2. And then we can move our exponents down in front. And we get 3 times log base 3 of z plus 1/2 times log base 3 of x. All right, and then condensing, we're just working it the other way now. We want to condense it into a single logarithm. So look for any numbers in front that are being multiplied times the logarithm, because we can move those to exponents. And then we're going to condense it into a single logarithm. And then if you're adding the logarithms, you're going to multiply the expression. So this will become x times y times z to the 6th power. All right, and then this bottom one, move the 12 to an exponent, move the 4 to an exponent, condense into single logarithm. Because we're adding the logarithms, we're going to multiply the expressions. So that's expanding and condensing. All right, so we're actually going to stop there tonight with this video, and because I think it might be a good idea just to do a little bit more review with logarithms before we get into the derivatives of logarithms. Okay? So we're going to stop there in the notes, and we will practice some more tomorrow in class. I will see you then. Have a good night.